Great, we are live. Hi, everyone, and thank you for joining us on Inner Join, the show where we dive deep into the world of data governance and data management. I'm your host, Shinji Kim, the founder of SelectStar. SelectStar is a modern data discovery and governance platform providing an automated data catalog, lineage, and documentation for enterprises. So today, I'm really excited to explore composable data systems with Julien Le Dem. Please comment on the chat if you have any questions for me or Julien. And Julien, welcome to Inner Join. Excited to have you here.
Thank you for having me. I'm looking forward to this.
We've known each other in the data industry for a while now, and you've done so much in this industry. One of, I would call, the OGs of big data in from the Hadoop days. So tell us, how did you get into data? Where did you get started? And how did you end up at where you are today?
Yeah, I kind of fell into the big data thing by mistake. So the company I was working for was acquired by Yahoo back in 2005. So I ended up working for Yahoo, and that was the beginning of Hadoop. And Yahoo was the company that was investing a lot in this project. They
Sorry,
had
what year
hired.
was this? And were you just a software engineer?
I was, yeah, 2005. I know I'm old.
Okay,
So
we've all
that
been there.
was 19 years ago. And I was a software engineer. Yeah. And so I worked for Yahoo, and I was working on a team building platforms on top of Hadoop and applying it to all the listing properties. So Yahoo Shopping, news, movies, autos, travel. So there's lots of acquisition of feed and matching, categorization, entity extraction. So you can build those guided navigations, right? And you can create links between various things. And so that's when, at the time, the way we do data engineering was not called data engineering. We use XML-based workflow engine to string together MapReduce jobs. So that was not super ergonomic. And at the time, there was this project called Apache Pig, which now kind of has been replaced by Spark, right? But you could do similar transformation. You have a nice DSL to do the similar transformation you do in Spark today. And we started using this as the better than MapReduce and workflows, XML workflows and MapReduce. So we could use this nicer language on top of Hadoop. And as a user, I started contributing to it and got hooked into open source, right? This project was very welcoming, and I became a committer. And then through that's how I got my next job, through this community, right? There was a strong community with Netflix, LinkedIn, Twitter, Yahoo. And I joined Twitter as part of their data platform team. So this one was more like using time series like people are used to do analytics. And I kept contributing to Pig, and I joined the PMC, and then was the PMC chair for that project for a year. And so that's how I learned all how open source works, how Apache works, how we make like a vibrant community. And then when I was at Twitter, I started the Parquet project in collaboration with the Impala team. So that was like the next step of creating my own project, which I guess was very successful. Yeah,
That's
and after,
amazing.
yeah, then I joined Dremio as a founding engineer, and that's where we created the Arrow project that has become also an important part of this composable data system. And later on, I started a company called Datakin, which is how we met, like competing a bit somehow, while being in the same VC dinners or parties. And we created this other project called Open Lineage, and like the focus was very much on how do we make Lineage easy to collect from the entire data stack, and how we solve Lineage for everyone, right? And being able to easily build product on top of that to solve data reliability, data compliance, all those governance, all those use cases that leverage Lineage as a building block. So it's been quite a bit of creating open source standards and really understanding the dynamic, how we align everybody's incentives so that everybody's successful and the project grows and is a success, right? Like it works because everybody needs this and we all win together building those open source projects.
Awesome. I want to dive into a little bit more of each of the projects, its origin, why this was created, and where it's going. Maybe if you want to share a little bit more about what you define as a composable data system, and for each of the projects, how they fit in that regards, and kind of their like genesis, that would be great.
Yes. So the composable data system is really a way to think about a database is a very complex system, but there are pretty clearly defined components inside of it. And these components are fairly tightly integrated, like in a vertically integrated solution to query data. And back in the day, if you needed to create a database, you would have to start from scratch and rebuild all those components. It's fairly complex and an infinite amount of work. And nowadays, they're pretty well-defined open source component that you can combine together and build a solution much faster depending on your constraints. So as part of that, the creation of Parquet for me. So I'm starting with this one because I was intimately involved
Sorry,
in it.
I do have one question about this.
Yeah.
You just mentioned that creating a database is actually a lot of work because you need to put together all these components together. Why not just buy with Oracle or SQL Server or DB2, which has been around back in those times too? Why do
Yes.
I have to put these systems
Yes.
together? Like, why did people start doing this and started creating open source?
Yes. So in a proprietary system, like let's say Oracle or something, everything's tightly integrated and very opaque, right? Like you have an API on the top, that's SQL. This is your interface. But everything is kind of tightly connected and you have very little ability to customize certain aspects. So of course, you can write maybe PL SQL, like stored procedures or things like that, right? But it's still very limited how much you can customize your system. And people add, you might have very different constraints, right? Like a database provides some good abstractions, some good constraints. So you're going to have atomicity, transactions, indices, things like that, right? Like, so you have a certain contract that gives you good abstraction to build software in a certain way, but that becomes very expensive depending if some of those constraints you don't actually need, right? Like, so we started inventing concepts like eventual consistency, right? Like, maybe you don't need like that strong consistency all the time, or maybe it's okay to have some like latency in the ingestion of data, or maybe durability is not as important, right? Like you may store things in something that looks more like a cache rather than something that's very durable and waits for the data to be synced to disk before returning okay on a transaction, right? So you have all those design choices that come in the database that is kind of all one package, and you have no knobs to decide what
Makes
changes.
sense.
They kind of generate like good abstraction, but there are tons of specific use cases, especially at scale, when it becomes very expensive or not scalable, and you can actually relax some of those elements. So that's where, when you have components, that's where building your own and picking various components and changing certain part of the implementation becomes useful or valuable to achieve the right characteristics, right? So some of that.
Makes sense. And I just to add, I think that this has become more of a norm for a lot of enterprises because there is a whole benefit to be able to just write the data first and then querying for later, querying in different ways or aggregating in different ways. And I think that's where it helps as well. If I am writing too much data into the database and it's eating up all of my IO, then that's not really great to make it a performance system. And I think that is where traditional databases can be limited, and there is no such thing as a one size fits all. So I think that the tightly coupled part plus wanting to scale in certain aspects, especially as more enterprises are collecting so much data now, events data, as well as just the ton of file data. It's I think that this is kind of like one of the reasons why it pushed enterprises to come up with uh, more decoupled systems around writing, reading, execution of queries, mail, management of files, so on and so forth. Is that right?
Yeah.
Am I
Yes.
understanding it correctly? Yeah.
Yeah, this is correct. And it's not, it's, and my statement about, like commercial products are not always a good fit. It's like, in a lot of cases they are, right? So it's just, they are like a pretty generic, and the one size fits all doesn't work. So it fits a lot of cases. And there are a lot of cases where you would use, commercial database, but there are some use cases where you need to do something else, right? And it's kind of open source brings more flexibility because you can actually change things. So you can actually look at the implementation and recombine. And it's interesting, there's a bit of a duality between APIs and query engines, right? And when you think of people building APIs where they're, it's like REST APIs or gRPC or those kind of things. And you see things in the API world happening like GraphQL. GraphQL is an API framework, but that kind of borrows from query engines on how it like joins together things from different sources. And in some ways, the composable data system is also a way of microservicing, like in some ways, your query engine. In some ways, so we can talk more about this.
Yeah, so let's dive into more of composable data systems. What are the stacks of components? And can you tell us a little bit more about different projects that as examples when I myself wants to build a composable data system, because the way that I want to run the queries, store the data is not going to be sustainable with a like one type of relational go-to database of the company.
Yes. So you were asking me earlier how Parquet got created, right? Or like those components got created, and I can talk a little bit about how Parquet got created. So at Twitter, we had Hadoop, and we had Vertica. Vertica is like a distributed database. So it's a database that is optimized for those analytical queries, like storing a lot of data and executing in parallel.
I would consider Vertica as one of the major, like a player of columnar databases.
Yes, exactly.
They
Right.
really
It's a
made
columnar
database to run well.
Yes, it's a columnar database. It's optimized for those OLAP analytical queries and to scale it, right? So at Twitter, we had those two, and on Hadoop, we could store more data, but the querying it was slower, where you would have high latency, it would take minutes. You could run huge queries, but it would take a while. And on the other side, Vertica was more interactive, but didn't scale as much as Hadoop did, right? And so one of the idea was, how can we make Hadoop more like Vertica? And of course, Vertica is a columnar store. And so it takes inspiration from this and from the Dremel paper that Google published. And we started building this columnar format for Hadoop. And that kind of started this, that wasn't called data lake at the time, right? But this notion, then you can put your data in a storage layer in a format that's efficient for querying, right, from various things, right? And around the same time, Vertica is still a design where you have a cluster and you store your data in your cluster. But then around the same time, Snowflake and BigQuery started being designed in a more cloud native way, where you separate the compute from the storage, where data gets stored in a blob storage in a columnar format. And the query part, the compute, is more on demand, right? And you can scale it independently. So in Vertica, you kind of have to scale kind of the original Redshift design as well, both compute and storage together, because you have a cluster of machines. In Snowflake, BigQuery, and the data lake architecture in general, you have this separation of compute and storage, right? So it's kind of one of the aspects of this composable is having this data lake storage layer separated from the compute. That gives a lot more flexibility on how you have resources and costs in scaling up and down, the ability to have parallel queries, better isolation, and all those characteristics. And Iceberg came on top of that to give a better abstraction on top of the blob storage and the columnar format. So that's
is there a certain use case that at Twitter you guys were using Vertica for versus Hadoop, and how did the introduction of Parquet enabled the Hadoop I guess pre-Hadoop data into other enablement of other use cases?
Yeah, so Vertica had the more interactive querying, right?
So for analyst queries.
Yes, for analysts, for anything where someone would do exploration on the data, like build dashboard or BI, right? You would have dashboards on top of it. And Hadoop was more for the batch processing and, we're going to do abuse detection, reporting, cleaning the data, like some kind of more massive, like machine learning tasks or things like that. But in the end, it's kind of, you create two silos, right? And it creates friction, because then sometimes there's data that's created by analysts that would be useful back in the batch system, right? And then if you don't have all the data in the interactive store, then it creates problems. So having a columnar format at the time in HDFS, but nowadays it's more in blob storage in S3 or GCS, enables this, how it's called lakehouse now, which kind of it's kind of merging the two worlds together, right? Like now you can have interactive query directly on top of your blob storage and avoid those two silos and make it easier to access all the data. And so that's really, this was the beginning of this, right? Like when we were collaborating with the Impala team, Impala was this distributed query engine on top of columnar files. And so the goal was to really manage to merge the two worlds, which we see nowadays, right? Like this notion of data lake and the Iceberg popularity is about that, right? Because when you use Snowflake or BigQuery, originally you still had to ingest your data into the system, even though it's built on top of blob storage in S3 or GCS. But nowadays, thanks to Iceberg, you can connect better those two, and they can work directly on top of a data lake and have better interoperability with these different tools people are using, whether you're using Spark or machine learning framework or a query engine that might be open source or proprietary.
For the audience, can you explain a little bit more about how the Parquet, so now you've explained how the Parquet format allows the columnar data in the blob storage, and how Iceberg or Delta Lake format runs on top of it, so that it is integrated with running SQL or Spark, things like that?
Yes. So the principle of columnar storage. So when you do a query, there are multiple benefits. When you do a query, usually you query a subset of the columns in your table, right? So columnar storage lets you very efficiently read only the columns that you care about, because instead of storing by rows and you do a lot of little skips to skip the data, and that's not very efficient reading from disk. You can read big chunks of the entire column you're interested in. And also, because you store one column at a time, it compresses better because you have more of the data similar together, and you can have better encodings that will compress and be a lot faster to decompress as well, because they're more specific to the data and you have one vector of data, and it enables vectorized execution, which is also faster. So there's a whole host of advantages of a columnar format that enable a query engine to access data much faster from disk. Now, Delta Lake and Iceberg both provide also what I would call snapshot isolation semantics on top of the data. So if you just have files in a file system like we used to do, it's a bit inconvenient, right? You need to have a bunch of conventions that if I'm adding to the table, I'm adding files to it, right? But you need to have conventions on what's an atomic append to the table, right? If you have distributed processes that write different files in a folder, and you have another query that reads from it, you need to have good semantics of what's an atomic append to the table, and not like real partial data, and not be sure what you read, right? So Iceberg and Delta Lake provide those nice semantics where they have metadata in the table format to decide what's the current version of the data, what's the next version, and atomically updating the current version of the table, so that you can append or mutate a table while another query is reading it, and the other query will have snapshot isolation semantic that it's currently reading a certain version of the table, and it's not going to see the new version until it's finished, right? It's kind of, this is the version I started reading, this is the version I'm seeing. And so you can have better consistency, more like a database, right, on top of files in a file system. So that's why they provide, time travel semantics, because in the metadata, they keep track of what files make what version of the table. And this is actually a version storage, right? So you can read the data as it was a certain time ago, as long as you don't, at some point you need to expire old version, but as long as you don't do that, you can travel in the past as much as you want. And you also can read a particular version without reading partial data while it's being updated, right? Because you're reading an old version and the new version will become visible atomically. So that's the benefit they provide. And that's why it's really important, right? Like when you have a distributed system with a lot of people reading and writing, you need this consistency. So it's like, some kind of transaction, but at the granularity that makes sense for a big distributed system, right? Like, so you can implement it efficiently, not in a very costly manner, like at the raw level.
Yep, for sure. So I guess if I were to put together a composable data system on my side, what are some of the trade-offs that may be involved in designing this type of database? And we primarily talked about Parquet and the but I'm wondering also if there are other formats that you think that you might want to mention as more of a columnar database or columnar format. And columnar databases does help with most of the analytical workloads. But are there any other formats or that you would also might consider depending on use cases because of
Yeah.
the trade-offs that you might have to make?
Yeah. So in a composable data system, you can have multiple storages, right? And multiple types of storage. So Parquet Iceberg is one type of storage that is optimized for bulk updates, right? Like, so it's for an environment when you're okay adding some latencies and doing bulk updates rather than inserting rows one at a time, right? And having more like high throughput transactional system. So it's really it's a good storage format for analytical queries, like you said, right? You're okay having some latency on ingestion, and you do bulk update, and the benefits of those bulk updates, and they're a lot cheaper to create, and then you can query on top of it very efficiently. So if you have different constraints, like for example, low latency ingestion, or so let's take the example of low latency ingestion. You may want to use something else, right? So and typically that's where people implement like a in-memory storage layer. Maybe you'd have a tier storage where you need to actually ingest the data as soon as possible. Or maybe you implement some transactional system that when you accept the data in, it is visible immediately in the query engine, as opposed to have latency and not needing consistency between your insert and your queries, right? If you don't need to read your write semantic, you can have bulk insert when someone writes and someone else reads, right? You don't need to read your writes. But if you need something that has more read your write semantic, when you wrote something, you know you're going to be able to see it immediately when you query, then you need a more transactional system. And sometimes you could do something in memory, and that's where it becomes more expensive, right? Or you might be using a different storage layer, like more of a database rather than file format in blob storage. So that's one big constraints you might want to decide. Do I need to read my writes? How much latency do I accept? And does it need to be transactional, right? So for example, something for transactional system, RocksDB has become a big, a popular way to do this with a write-ahead log. And then that's where you would have a system that's more row-oriented, right? Because by definition, a columnar format, because it stores one column after the other, it can only store a row batch or a row group together, right? You cannot store one row at a time because it needs to decompose those rows into columns to write one column at a time. So by design, it needs some latency to be there. So RocksDB is a more row-oriented format, but that's where you can commit the row immediately and see it right away. So typically in a system like that, you would have two tiers, right? And kind of recent data would be in a row-oriented, and then it gets turned into a column-oriented format. Or maybe you're writing to arrow batches in memory, and then eventually gets written to a Parquet format for more historical data or after a certain time. So that would be an alternative to this design. And so that's kind of the bottom layer, of the composable data system. You may have multiple storage layer, and typically in the composable database, at the top you have the language, right? So maybe it's SQL, maybe it's data frames, right? So it doesn't matter too much, and then that gets parsed or transformed into a logical plan. So typically that were Substrate. It's another open source project that standardizes the plan of the query. So you have a logical plan, which is a representation for the transformation is. It goes into the optimizer. So that's where you have a project like Calcite, for example. Calcite is an open source, Apache Calcite is an open source project that is an optimizer framework. So you can optimize to create a physical plan that will execute on the query engine. And as part of this transformation by the optimizer, it's going to take your query and extract filters or aggregation or limits to push them as much as possible to the storage layer, right? So that's where I give the example with Parquet when you can do projections push down, which is reading only the columns that you need to read, right? In your select, you're selecting A, B, C. The optimizer, we know those columns come from this table. We're reading only those columns from this table. So I'm going to rewrite the plan in a way that tells the storage layer, read only those 3 columns. If there's a filter, it's going to extract the part of the filter that applies to this table. And we can use the statistics in the storage layer to skip a whole bunch of data and not read from disk what we don't need to read from disks. So that's where you have the optimizer, and then you have the storage layer. And in the storage layer, usually you need the ability to do those push downs, so projections, knowing which columns to read. Predicate, so what is the filter you're going to apply to this data, and use the indices or statistics and things like that to skip data you don't need to read. Aggregation, so if you're going to just count things, you don't need to read all the data to then count in memory. You can just push the counting or summing all the way to the read layer that's going to read from disk. And limits, right? If you're going to say, I don't want more than 50 rows in my result set, you can push that all the way down to the reader, and then we don't need to read more than that many rows that match the filter, or if there's no filter, that many rows total. And so that's kind of, this is an important abstraction, but because that's how you can build a storage layer in that database that's going to be integrated in a performant way with the rest of the engine, right? So, and that's where Arrow, so Parquet is the good standardization for storing in blob storage. In Arrow is a good standardization for returning data from that storage layer. If this is something more for like a database that has maybe multiple tiers, or like as a transactional abstraction, or this kind of aspects. So it's kind of the various layers of this composable database or deconstructed
Yeah,
database.
and in a way, many times this is like a format, right? So for Apache Parquet, okay, I think one of the reasons why it's being used everywhere is because it's a format you follow, and then you can put it in like blob storage, like S3 or GCS. Now, the coring system, whether that's on the logical plan side or physical plan side, I think there are also a lot of services that allows you to do this, like Athena or I guess Presto. I might be just like mixing them all. Maybe if you can also share some of those components and how they fit together to run on top of the storage layer, that will be helpful, because I think a lot of our audience are more used to those services that are provided by cloud providers and whatnot.
Yeah, that makes sense. So yeah, they, like when we talk about those components you can recombine, there's two very distinct categories. On one category, you have Parquet Arrow substrate, which are standard formats or standard models. So that's what enables combining the components together, because they create the contract, right? So Parquet is the contract from the blob store. Arrow is the contract for the in-memory or cross-service sharing of data in an efficient way. Substrate is the contract on how you define your plans or your filters or your expression and all that. And then in between, so that defines the boundaries between the components. Then in between, you have components that are like more like an execution on an orchestration role, right? So Calcite is the optimizer, is kind of the orchestrator that knows how to plan the query or the transformation. And something like Data Fusion or Velox is the main part of it is a compiler that knows how to efficiently execute a certain piece of plan. And so, you know, you have those pieces that kind of fit together. And then if you look at those proprietary system, like if we think of Snowflakes or BigQuery or Athena, this notion of data lake, really, they will also respect the same API so that you can have a proprietary system that's more opaque and you don't see the component, but they're capable of integrating with a storage layer that has the proper abstraction, right? That's where Iceberg and Parquet become a good abstraction of the data lake, and you have this kind of open data lake where you can plug various systems. And now those proprietary systems, databases can efficiently interact with the open source component, right? And you can have a more open storage of data. You own your own data, and you can query from different things. So Athena is based on Presto, right? Like it's a proprietary service, but that's based on an open source project. Snowflake and BigQuery are entirely proprietary system. Presto is an open source project that came out of Facebook. It was open source by Facebook. And Trino is, so at some point the project forked. So you have now two projects with Presto and Trino, but they came from the same origin. And Starburst is the company behind Trino that offers also proprietary product that build on top of it. And similarly, Spark as a Spark SQL when you can run SQL, and Delta Lake and Iceberg as two similar components that provide this data lake abstraction, right? So you can have a nice storage in S3, but has some isolation semantics. It's not just files in a file system. And then you can plug various product on top of it and keep those nicer semantics. So it makes your data lake look like a warehouse where you have tables and you can have some governance and who has access to what, and so on.
Yeah. Makes sense.
Yeah.
So in between those, do you see any particular performance trade-offs or types of like volume or latency differences based on the use cases that people are trying to run? Or do you see it as more of a user experience and differences in how like the querying engine is embedded in different services? Because in some sense, they all do the same thing. Like they all interact with Parquet formats and now Iceberg, and but there may be certainly a big difference between the user experience of how the queries can be supported and managed on those systems.
Yeah. So typically, some of those things started from a more vertically integrated stack, right? And so often the experience, they offer a good experience within their ecosystem, right? Like on the Google side, you have the, like originally you had a good experience, you ingest data in Google in BigQuery, and you can query, and you have your access control and everything in your console, and you have a nice vertically integrated experience. And on the Datadog side with Spark, you have a similar thing. You have a nice vertically integrated experience, and same for Snowflake. And as long as you stay in that vendor ecosystem, everything works well together. But usually people, they start, oh, but we need to use this open source machine learning framework, right? And we need to use this. And we also, usually people do start needing other things, right? There's this nice walled garden of a vendor, and they start needing other things. So that's where this data lake or lakehouse pattern became more prominent, because people were like, well, I like your stack, but I also need this and that. And as soon as I get out of your walled garden, these kind of things become hard to use, right? I need to export data, import data. You get back to this siloed experience. And so that's where the separation of saying, well, you can have a data lake and maybe you use Delta Lake or Iceberg or something else. And you're going to be able to have the nice integrated experience, but at the same time, we're breaking the silo, and you can still, interact with other tools without this being an export and import experience. It's very not the best experience for the user, right? So that kind of drove this moving to things. So you would say, yes, sure, it's a distributed query engine, and there's always a race, right? A query engine is never finished, right? You always have things you need to optimize. There's always this corner case where one will be slower than the other, and they're kind of competing, and it's always improved. So overall, it's all the same. There's always going to be a reason why one will be a little more expensive in some cases, or a little slower in some other cases, right? It's kind of, those are very complex systems. So of course it's never apples to apples. But I think it's more about how we make it, more flexible, to use different things together as well, right? And not being tied to one vendor stack. Like, people really don't like vendor lock-in, and it
Sure.
works both
That's
ways, right? Yeah.
Yeah, and I think a lock-in is one part, and then the other part of it is, moving data is expensive. The
Yes.
egress that you have to pay is very expensive. So,
Yeah, that's a very
uh,
good point.
and
Yes.
there's always a lot of data to move, because having just partial data, you won't be able to get the full insights that you want. So I think in this, like, move to more like a zero ETL, being able to query other external systems directly is very important. And the standardization of the file formats and like something like Parquet and Iceberg is hence really helpful. Now, still, in order to manage data on top of multiple systems, I'm curious to hear your thoughts on, like, the role of metadata. Metadata
Yeah.
is something that describes the data, and we usually access it as part of information schema. But I feel like the whole movement with Iceberg is also part of making that technical metadata more, usable and, aggregated, right? But also, like, so curious to hear your thoughts on that, as well as the metadata that is now being exposed more to the querying systems and the logical side of execution of data retrieval and aggregation.
Yes. So that's another very interesting topic, right? Like, so, um, I think if you look back a while ago, right, it's been very hard to extract metadata or know or have visibility on how data move from one place to the other. And there are tons of reasons why you do need to understand lineage and this technical metadata, right? If you care about data reliability, data quality, you need to know where the data is coming from, right? How changes somewhere in your dependency graph impacts your data. So really understanding lineage and where the data is coming from. If you care about GDPR compliance, you need to also have lineage to know where your user private data is going. Is it going in the right place? Do you respect what you said you were not going to do, and things like that? And general governance of understanding how data flows. So historically, it's been very difficult. Like, basically, you had to reverse engineer every system to kind of like extract what's happening and where is data going, or people would manually document and you were never sure it was up to date. So that's where Open Lineage has been a way to solve this, right? My perspective on solving this problem is that the only way we're going to make it tractable and not just like everybody's trying to reverse engineer and manually extract lineage and this being a moving target because old system works and those reverse engineering break all the time, we're going to adopt a standard as an industry and makes this like just built in. Every data system should have built in exposing what are all the transformations that happen, what's the lineage, where is this table coming from, and expose that natively in a machine readable, technical lineage, like operational lineage perspective. And so that's where we started Open Lineage, and this is the only way I know how to move the industry forward in a certain way. We use open source, we get together and we bring more people. You find more like-minded people who see this as a problem, who are willing to help solve it. And all you need is to create this focus point where people can say, oh, we always needed this, why didn't we have it before? Well, someone needs to get pushing the thing so that it happens. And it's happening, right? Open Lineage has started becoming the standard on how you expose lineage across everything. And when you think about this composable data system, right? I talked about the optimizer that creates a plan, right? So the optimizer is kind of the brain of the query engine, and you have the logical plan that is a representation, programmatically readable representation of what the transformation is. So you can plug at this level and extract what the lineage is, and as a more technical lineage, and look, this table was derived from that table. This is where this column came from that column, and this is what the expression is. So I can tell you whether we kept the same value or it's been obfuscated. Maybe it was a PII column and we hide it in this query, so you know that it's not going in the output. Or you have column lineage, so you know we didn't read the PII in this query, right? And you don't have to worry about this. But in this other case, we read the PII and it got written in another table, and so you need to propagate the tags and things like that. And so that becomes built-in. And like, for example, for Spark, you know, the way OpenLineage extract, it plugs in a query execution listener, gets the logical plan, turns that into lineage in a standard way. In Airflow, it's also built in of each operator expose its lineage in this standard representation. It works for various, query engines and extracting lineage. And so that's, like to me, the foundation of enabling all those functionality. And maybe vendors will have product for data quality, data reliability, compliance, governance. But the foundation for all those things to work in the ecosystem is actually standardized instrumentation of all your data transformation, right? So that's kind of, that's been the approach, right? So from a technical perspective, we instrument everything. And then from a use case perspective, you will have various use cases. Like nobody needs lineage for lineage. They need lineage for data reliability. I need to know that this dashboard or this report that we send to our customers is correct. And I want to know when something's broken, be able to find quickly what impacts, right? I need to be able to know that everything upstream from this data set is working correctly. And in compliance, I need to know that where my user private data is going, or I'm a bank, I need to be able to prove that the data sent to the regulators is correct, because I can look at the lineage and prove that everything upstream is working correctly, and then I understand it. So there's a bunch of use cases that drive the need to understand lineage, and you can build different products on top of it. But the underlying foundation is a good modeling and instrumentation of this technical lineage, of knowing there's this transformation that ran at this time and read from this table those partitions and wrote those partitions in this other table, in a very precise model.
Yeah, one thing that I've noticed from integrating with OpenLineage from Select Star is that it does expose a lot of details of almost like the query plan side of the job itself. So I think that gives the all the kind of like the technicalities and the accuracy of how things work. Today, this OpenLineage primarily works with like Airflow and Spark, more or less by users adding the OpenLineage, like almost like a library into their code, right?
So
Can you explain a little bit more how
yeah,
it works with external systems today? Because
yeah,
this OpenLineage is beyond just the standard. There are components that
yes.
people implement, right?
So there's two aspects. So one aspect is the spec, right? What's our standard representation of lineage and all the metadata that goes with it, like column lineage, data quality metrics, PII labeling, all these kind of different aspects. So that's where OpenLineage is this notion of facet. So we can model all those different concerns around the data, or profiles, how long it took to run, and so on. And the other aspect is integrations, right? So there's a Spark integration. So, and the goal of the integration is to always take this instrumentation approach, right? The goal is not to ask each owner of a transformation of a query to fill in the lineage. The goal is to instrument the engine and to see all the transformation that goes through, and to automatically export lineage, right? So when you use Spark, there's a plugin. Spark has this notion of query execution listener. So basically, either in your Spark cluster or in your command line, you always add the plugin. you can package it in the way you use Spark, for example, and it's always instrument every Spark job, and it sends open lineage event of all the transformation using looking at the logical plan in the execution. In Airflow, we actually made this built-in Airflow, right? The eventual goal of open lineage is to be just a specs. So today there's a bunch of integration. There's a Flink integration, there's a Spark integration, there's a DBT integration. There's a bunch of integrations like this. But eventually the goal is to be just a spec, right? So for example, for the Airflow integration, it's been moved. We now deprecated the open lineage Airflow integration because all the logic is built in Airflow. So Airflow has an open lineage, Airflow open lineage component. So you just turn it on in the configuration. And Airflow is going to start sending open lineage events. So in that case, the users don't need to know about open lineage, right? All their jobs that are running in Airflow will start sending lineage information about what's running. There's still certain things that are opaque, right? If you write Python code that is a bit arbitrary and you don't use any common data abstractions, then it's a bit opaque to lineage. So there are always limits of how much you can instrument automatically, right? It's better to use a standard way to access data. But otherwise, in a lot of cases, and it's always improving, but in a lot of cases, you get lineage automatically out of your system. And so that's the goal, right? Really this notion of instrumentation.
Sure. And I think lineage is definitely one major part of metadata that you need to keep track on, especially when you're not getting, let's say the query plan directly from the data systems, because you are basically just like running the query on top of the file system, and there may not be the best way to trace how the data has been retrieved in the past. What are some of the other metadata standards that you would recommend our audience to keep track of across the data systems? Are there other areas of metadata that you feel like is important to catalog and understand in terms of the management of the data?
Yes. So, there's this notion of data catalog. And it has a bit two meanings. One meaning is like people being able to have a UI when they can discover what data set they have, and there's a catalog they can consult. And the other side is a more technical component, which is more like a programmatic API where you can see all the tables that exist. It's kind of more the data, like actually like a database, right? Like, so for example, as part of Iceberg, you have a REST API, the Iceberg catalog, that has been implemented in a couple of areas. For example, Unity catalog implements this, right? So Unity has this dual notion of being the actual metadata storage layer for the database, as well as a UI or something you can consult what exists. So there's this kind of notion, like in the semantic web area, there's some good metadata about how to think about data set, but it's not necessarily well integrated in the data world that we understand. But some catalog vendors use those notions. Yeah, it's going to be interesting how to see the Iceberg REST catalog. Like another Project Nessie, is also a catalog that adds some cross-table transactional notion on top of Iceberg representation, the Iceberg contract. So Iceberg has kind of this per table transactional, somewhat like at the bulk level. And then Nessie adds this cross-table transaction where you can say, oh, now I'm going to make visible all those tables, these updates to all those tables atomically at once. yes, is that what you had in mind in the notion of what are all the things that exist?
Yeah, I mean, especially for when the companies are putting together their quote unquote composable data systems, then it is also
Yeah.
important for them to keep track of that metadata, because it's
Yes.
not in one system. Like, I go to Snowflake and I
Yeah,
get all
that's
the
a great
catalog
point.
from there. So it's on the customer, or it's on each of the companies end to keep track of that metadata, and anything that has happened on top of that metadata, which is kept separately. Is, I
Yes.
think, kind of where I'm coming from. So, like, what are the areas that you can use? Obviously, yeah, like you mentioned, you can use a notion of a data catalog that pulls all of this from multiple systems, put it in one together, or you can also look into the specific technical catalogs of the file systems and others to keep track of it.
Yeah, so there's like very two distinct categories in this
Right.
metadata. So one, like the REST catalog aspects, the iceberg REST catalog, right? The catalog like you would have in Unity or Iceberg, which
Yeah.
is really a component of this database, right? Like when you have the query, when you type your query and you have the optimizer that takes the query to turn it into a plan, it's going to talk to the catalog to say, hey, what is this table? What is its schemas? Give me some more information about it, so I can make a better plan. And on the other hand, the open lineage aspect I was talking about is about metadata, about what happened, right? The transformation and keeping track of lineage, how this table got derived into that table. And those two things are complementary, right? They kind of connect. You have the operational lineage of what is the state of the data, but also how it's been derived from other tables. And I think
Right.
those are very
Yeah,
important.
which I think both are, yeah, complementary and important to keep track of. So I guess looking forward, what are some of the things that are upcoming in Parquet projects and others that you are part of, also like Open Lineage? And as you are thinking about the next 3 to 5 years of how companies will be interacting with data going forward.
Yeah, so in the Parquet, there's a lot of activity at the moment about, there's like a moniker of Parquet v3. But the goal is not to actually make an incompatible major release of the format. The goal is to improve the format, and some of the concern are making sure Parquet works for very wide schemas with a lot of columns. So improving the metadata. And the other aspect is adding a few encodings to improve certain use cases, in particular time series or things like that. There's some different research papers that came out in the past couple of years. I mean, discussing like newer encodings to make this even faster and better for some of those aspects. So this is happening. On the open lineage side, there is the ecosystem has been growing, right? It's been adopted by Microsoft, by Google, recently by AWS for their various catalog. I've been talking to different companies. There's a company called Foundational that looks into how do we make sure your data goes in the right place, like, the tag propagation and this kind of information. There's a lot of the interesting. I'm following also how the data mesh is becoming a reality, where this notion of data mesh, where you treat data as a product, right? And it has certain properties, and it's not just tables and that get derived from each other. And so Next Data is the company that is implementing the data mesh. So it's interesting to see how that goes. And really, when you think of data mesh and having pieces like just a service mesh with a bunch of services depending on each other, and you use tracing to understand how requests flow from one service to the next. In a data mesh, you use lineage to understand how those data products depend on each other, and it's kind of built in. And that's where open lineage becomes this equivalent to tracing, right? Like, and it's kind of instrumenting and connecting everything together. So I think those are interesting developments to see happening. Yeah, and the Arrow also has a lot of activity, especially in data fusion. Data Fusion is this embeddable query engine that you can use. That's one of those big components, right? You can use to do efficient plans on top of Arrow, efficient execution on top of Arrow. And Data Fusion is being used in a lot of places. I've seen it used for a time series database, for a streaming query engine, for a re-implementation of Spark, right? There's this Comet project, which is taking Spark and switching the physical plan for using Data Fusion and making it faster. And there are multiple re-implementation of Spark, right? Like one is the Databricks Photon engine, which is a more efficient proprietary execution engine for Spark. Comet is an open source, came from Apple, implementation on top of Data Fusion to make it faster. And there's a Rapid Spark project, which is running Spark on top of GPUs. That is an open source project led by NVIDIA. So there are kind of interesting various aspects of the Parquet, Arrow, Open Lineage project, and then like interesting developments in these areas.
Yeah, lots of exciting developments coming up. So Julien, really excited to have you here, and thank you for joining me today. I learned a lot, and I'm excited to push this out as a write-up soon. Yeah, please, anyone that's more interested in the development of Parquet and others, please follow Julien, and I will see you all at the next Inner Join. Thank you again.
Thank you for having me. Bye-bye.
Bye.